CLI and a cross-platform IDE for C and C++. Download now.
Hello, everyone, and welcome to my talk in C++ Online. I hope that you've been enjoying the conference so far. I think the online conference is a great design. Everyone can just attend from their homes. It's a great conference to reach wider audience, and it's quite promising to see the conference growing from last year. So today I'm going to be talking about a very exciting new feature in C++ 26, and hopefully get all of you as excited as I am about it. The feature is called reflection, and the talk is aimed at fundamentals of reflection and going over all the basic pillars and the syntax of reflection. There's going to be a lot of examples in the talk, a lot of coding. So I'm hoping to make it a bit more of an interactive session. If you have any question in between the talk, please feel free to raise your hand via Zoom, and I'll try to unmute you and you can ask the question. So before we get into the talk, a bit about me. I'm Sarthak Sehgal. I'm a tech lead at Maven Securities, which is a high-frequency options market-making firm. We've got offices in Chicago, London, Amsterdam, and APAC. So if you're ever interested in the space, feel free to reach out to me. Just get in touch via Gather Town or LinkedIn. Now, bit of an overview of the talk, what I'm going to be talking about today. Firstly, I'll start off with what reflection is. Then, before jumping into C++, we'll see how reflection has been implemented in some other languages. There are languages that have had reflection for over decades. And although C++ has been, like, the committee has been discussing reflection in C++ for a long while now, finally we're going to get it in 26. But this is something that has been almost decades in working. So we'll see how reflection works in other languages, just to compare the implementation in C++ and the feature support in the first C++ implementation. Then we'll see how reflection worked before C++ 26. It wasn't exactly purely reflection because the language did not have native support for it, but there were still very clever workarounds to achieve what reflection tries to achieve. So we'll have a look into how that was done before C++ 26. Next, finally, we'll jump into reflection in C++ 26, talk about the fundamentals of reflection, what the syntax is, get everyone familiar with the syntax, and look into a lot of examples and truly appreciate the power of reflection in the language. Then we look into some examples of examining code with reflection, and finally generating code with reflection. Now, I've been talking about reflection a lot, so let's look into what reflection actually is. So fundamentally, reflection is the ability of a program to examine itself. This could either be inspecting the program or modifying it. And specific to C++, C++ is going to have something called static reflection, where the compiler exposes structure at compile time. Now, what exactly do I mean by the ability of a program to examine itself? Let's consider an example where you have an enum. Let's say you have an enum of colors. There's like 3 elements, red, blue, green. And in C++, you've defined this enum class. And what you want to do is, say, iterate over the elements of the enum, or convert one of the elements of an enum to a string, or say provide this function where you pass in the enum element. Say you pass the blue color enum, and you want to return a string. So things like these, where you are actually examining the code itself. So you define an enum class, but now you want to examine what the elements of that enums are. You want to iterate over those elements or convert them to a string, get their identifier. Or let's say you have a struct in C++, and you want to iterate over what the data members of those struct are. What you're essentially trying to do is that you're trying to examine the code that you've already written in C++. So that is what the examining part is. You may also want to do something like generating code based on the existing code that you've already written. So you might have a struct. You might want to get a list of data members of that struct, and then generate a new struct programmatically, not by writing all the whole new structure of the struct, but more programmatically, using a different struct. And you may want to create a new one. And that is where generating code using reflection comes in. So essentially, all these data types or variables, what they're doing is they're or our program is reflecting itself at compile time. Let's have a quick look at an example. You don't have to worry too much about the syntax as of now. We'll take a much deeper dive later. But in this example, this is something that is supported in C++26. I have an enum called color. It's got three colors, red, green, and blue. In the first line, what I'm doing is I'm using the reflection of this enum to get the identifier as a string and print it out as stood out. So this is something that wasn't natively supported pre C++26. And now I can simply print out um, the string name of a enum or a class or a struct, and things like and various other entities. In the second line, I'm accessing all the elements of this enum. So I'm calling this enumerators of function, which gives me all the elements of this enum. Then I'm accessing the first element, which is red, and printing the identifier of that. This is quite powerful. Now I can get a list of elements in my enum, iterate over them, index over them, print their identifier, and various other things. This is just to give you a taste of reflection and what it tries to achieve. But we'll go into a much deeper dive in a few slides. Now, before we consider or look at reflection in C++26, let's have a look at some of the languages, in particular Java and Python, and how they implement reflection. There's been support in these languages for a long while now. So consider this code in Java where I have this class foo. There's a simple method in the class called print. All it's doing is it's printing hello world on standard output. I can do something similar in Java where I'm getting an object of the class called obj. Then I'm getting a class from that object with the .get class method. Java provides this method for all objects. I can do something similar as in the previous example where I was trying to print the identifier of the enum. In this example, I'm just calling myClass.toString, and it returns the identifier of the class. What it's going to print is on the right side. You can see it's going to print class foo. Java also provides a simple method to get all the declared methods of a class. I can simply do myClass.getDeclared method, and Java will return a list of methods of that class. This is something quite powerful, and this is what C++ tries to bring as well, where you can get access to the structure of the program that you're writing now. So we can get a list of declared methods and declared data members and things like that. In Java, we can also do something like having the user input a method name and invoke that method name at runtime. So let's have a look at this example on Compiler Explorer. Okay, so what I have here is I'm asking the user to input a method name to be invoked. Then I'm just getting it from the standard standard input, and what I'm doing is I've created an object similar to the previous slide, getting the class, and the main thing is where I'm now able to just get the method from a class by the string name. So if the user inputs a valid method name, in this case print, it simply invokes that method and prints hello world. But let's say the user inputs an invalid method name, say print non-existent, it's going to return an exception, no such method exception. So this is exactly where reflection is happening, where we are now able to get a method from the class by a string name. The important thing to note is that in Java and in Python, reflection is runtime, where you can call get method, for example, which is like a meta function or a function related to reflection. You can call this with a runtime string. Whereas in C++, reflection is static. We'll talk a bit more about that later. But essentially, everything that we are operating on in the reflection world needs to be available at compile time. Whereas here, I can call this get method with a runtime string. Let's also have a look at reflection in Python. Again, Python has a very rich support of reflection. Let's say I have this class called order. It's a very simple class. It's a data class. It has two members, price and quantity. And Python provides some utilities to print the data members of the class. For example, I can call the dir method. I've created an object of this order class. I can call this method, and it returns the data members of the class. We can also use setAttr, which means set attribute. What it's doing is it's setting a new attribute in the class. So I'm adding, I've already got two members, price and quantity. With set attribute, I'm adding another attribute called update type and assigning it to a string new order. And if I print the updated object, I can print keys and values, price 100, quantity 5, and update type new order. Now, this printing of the updated object is quite interesting and powerful. Python provides this method called vars, which you can use to simply print all the keys of the data members, or rather the identifier of the data members of a class and their corresponding values. This is almost like serializing the class, and this is something that C++ has struggled or has had the poor support for in a long while. Given a class, it's very common to be able to serialize that class, print out the data member keys and their values on standard output or for logging. And without reflection, this was not an easy problem to solve. There was a lot of workarounds, a lot of macro magic in order to be able to do this. But with reflection in C++, there's simple and native support for serialization, which we'll see some examples of that later. But it's something that is very powerful and makes us appreciate a reflection a bit more. Python also provides get attribute similar to set attribute, where you can get the attribute using a string. This is similar to get method in Java, where we were getting a method by a runtime string. In Python, we can also do something like executing a code that is a code that is in the form of a string. In this example, this code is available like in the code itself, but you could imagine inputting some code from the user and then executing that using exec in Python. So in this example, what it's doing is it's getting the fields of the class using vars that we saw in the previous slide. Then it's describing then it has a string code, which is a method def describe. All it does is it prints the fields, or rather the keys of the fields, so price and quantity. And then it's defining a namespace, executing this code in the namespace. With exec, this code is now converted from the string to actual Python code. So it's executing the string as code. And then I'm setting an attribute in my order class. I'm calling it describe. And this attribute is going to be the method that I just executed. So when I call o.describe, it's going to now invoke the method that was initially a string, and it's ultimately going to print price and quantity, the keys of the fields. This is something very interesting where now we can execute code at runtime. And again, this is something that if the string were a runtime string, this is something that C++ would not support. Now, having looked at reflection in Java and Python, let's have a look at how reflection would work pre-C++ 26. Before C++ 26, these weren't exactly, there wasn't exactly a pure support for reflection. There were some workarounds that generated code to achieve reflection-like behavior. So it wasn't really pure reflection, and you might have come across a very famous library, which is a C++ 14-based reflection library by Boost called Boost Describe. This is widely used in the code base that I work with at my company, and I'm pretty sure a lot of people might have come across this. It's a very rich library that provides reflection in C++ 14, and how it achieves this is a very sophisticated usage of macros, and we'll have a small look at that. And although I'm not trying to go into the details of how Boost Describe works, let's have a look at how reflection-like behavior could be achieved before C++ 26 in order to appreciate how simple the language support in C++ 26 actually makes reflection. So what we are trying to do with the next example is ultimately we want to achieve a method which can be provided an enum, and we want to be able to convert that to a string. So we want a method enum to string with an input enum. I want to return the string corresponding to that element. To start off, let's say I define a macro hash defined colors. This macro takes in a function and invokes the function on these three literals. The colors are red, green, and blue. So what it expects is the user to provide some sort of a function, and it's going to invoke that on these three literals, red, green, and blue. Next, I have this enum class color. This is C++ enum, modern C++ enum class. And what I'm doing is I'm defining a function for my macro, and the function is simply name, comma. So all it's going to do is it's going to expand, or it's going to it's going to invoke name, comma, take the literal name, add a comma to it for each of the literals red, green, and blue. And it's going to So ultimately, what we'll expect to see is red, comma, green, comma, blue, comma. And then I have hash undef, which is cleaning up the hash define, just so that the next lines of code is does not have the function defined. So let's also have a look at this in Compiler Explorer. And in fact, what we can do is we can check out the preprocessor output to ensure that this enum is correctly defined. So in here, I have the enum from the previous slide, which is hash defined colors. I mentioned that it's defining a macro called func, which takes a function called func, and it's applying name, comma, to each of the elements. So what I expect to see is red, comma, green, comma, blue, comma, an expansion of this. Now, in Compiler Explorer, I can do -e to look at the preprocessor output. And let me just make sure I have a compiler instead of executable here. And if I do -e, nice. So you can see that when preprocessor parses this, what it outputs is enum class color with red, green, and blue. And this is what we exactly expect to see and want it to do. So now with the macro, I programmatically define an enum. And next, what I want to do is provide a function enum2string. Let's get back to Okay, so we've seen this so far, so good. We've seen the preprocessor output. What it returns is the enum class color with red, green, and blue. Next, similarly, what I can do is I can define a function enum2string, which uses the same macro. And instead of simply defining the function as name, comma, I can do something like this, where I have a switch case statement. At the top of this method, I have switch C, which takes in the enum being the enum parameter C, and and I'm now programmatically generating the cases corresponding to the switch statement. So what I'm doing now is that I'm calling this macro with the function case color : name. So it's going to simply expand to color red, color blue, color green. And then whenever one of the case matches, I want to return a string corresponding to that. So hash name essentially um, just puts quotations around the identifier. So we have this literal red, blue, and green. We want to put quotations around it, and that is what hash name does. It's just some macro magic. And once the case matches, we want to return a string. What this will look like in the preprocessor output is something like this, where again we've just expanded the macro to for the three literals, red, green, and blue, and we're simply returning the string. Now, this is quite interesting. We have now been able to define an enum programmatically using this macro, and also define an enum2string method. So I can simply do something like this, where say I have all colors available somewhere, which is the array of enums. I can simply print the string corresponding to each of these enums. Now, with a bit more of a macro magic, we can do something similar to what Boost Describe does. So in the previous slide, if you see, we still have to hash define our colors enum. Like each time client wants to define a new enum, they have to do like hash define colors with this function. It's not exactly pretty. We can make this a bit more prettier with some macro, more of a macro magic. And I'll show you a quick look of that, but we won't go into too much details of that. So again, this is some code that expands, that does something like for each for each parameters. Each parameter you pass, like there's a parameter pack, it does for each. But ultimately, what I want to show is we can do we can write some utilities using macros, and we can ultimately come up with a utility define enum, which simply defines enum with the name color, elements red, green, and blue, and this enum will now have reflection support. And this is exactly what Boost Describe does. It provides a lot of such macro utilities, which then provide reflection support for the enums or structs that we are defining. The enum to string is very similar to before. It just takes an enum as long as you've defined it using the macro define enum and is able to convert it to a string. Now you can see, just to convert an enum to a string, or like an enum's element to a string, it requires a lot of code. And to be honest, like a lot of code that most of us wouldn't understand in the first go. So this is quite complicated, and we'll soon see how reflection just makes it super simple. It's probably one line of code using reflection. Yeah. Okay, so we've seen this example where now we've been able to convert an enum to a string before C++26. I mentioned that Boost Describe is a very famous library, and we saw an example very similar to this, where in Boost Describe you can do something like Boost define enum class, um, have the enum provide its element, and now you can use the other utilities provided by the library for reflection over this enum. You can do something similar for structs and classes, where you can do Boost Describe struct. It takes the struct's name, the basis of the struct, and the members of the struct. Now, not going into too much details of this, but Boost Describe is a very rich library that provides a lot of reflection support. So now that we've seen how reflection or reflection-like behavior was supported before C++26, let's dive right into reflection in C++26. And I'll talk about the three most important pillars that I think are of reflection, or of getting a hand of reflection. And once we've done that, we'll consider a few examples of reflection. And this is where I want the session to be a bit more interactive. If you have any questions so far, or any question in the next few slides, just feel free to raise your hand, and I can help unmute you. Okay, so reflection in C++26. I think reflection has, to understand reflection, there's three most important things. The first is the reflection operator. What the reflection operator does is provides a reflection to various entities in the C++ code. These entities could be a type name, a variable, an enum, a namespace, and a few other things. And what I mean by providing a reflection over these entity is, you can think of the coding, like the code that we write, as one domain, and reflection as a separate domain. So once we enter the reflection domain, we can now operate on these reflections. For example, get the identifier of for an enum, or get the data members of a struct. And all these operations in this domain are limited to the domain. Uh, these operations in the reflection domain are done by something called as meta functions. So meta functions provide utilities to operate over reflection. And lastly, the third thing is splices, the splicer operator, which is again a new thing being introduced in C++26. What the splicer operator does is it helps us go back from the reflection domain to the C++, like the programming domain, and we can then use the reflected entities in our programs. And again, you don't have to worry too much about it. We'll go into much more detail in the next few slides, but it's an important distinction to make between the normal C++ program that we're writing and the reflection domain. And we'll soon see how to shift back from these two domains. So the first thing is the reflection operator. Here I have this code, context per auto r equals caret int. And this caret is the new reflection operator being introduced. What this operator does is it lifts the expression into reflection domain. And the entity being reflected can be a type, variable, function, namespace, an enumerator, and a few other things. It's informally called the unibrow operator because I think this, if you draw like two carrots with a dot in between, it almost looks like a face. And if you remove the dot, which represents the nose, you get just the two carrots, which is almost like a unibrow. So you'll see a lot of people calling it the unibrow operator. One of the things which you might have noticed is that in this expression, I've used const expr, and this is because the reflection expression should be evaluated at compile time. I mentioned before that C++26 introduces static reflection, so everything has to be available at compile time, and const expr variable are evaluated at compile time. And although I've hidden the type here with auto, the type being returned by the reflection operator is stood meta info. So um, this type is common for all reflection kinds. So no matter if you're reflecting a type, a variable, function, or some other entity, it's going to return a stood meta info type. There was a lot of discussion in the committee about whether there should be distinct types for distinct reflections, but ultimately they decided on stood meta info. My understanding is that they wanted a single type, so such that it's easier to maintain and it doesn't break backwards compatibility when the reflection evolves. And there's going to be a lot more changes to reflection. It's still very new in C++26, so it's going to be something that evolves much faster. And they wanted a single type so that it's more maintainable, more extensible. This, if you look at the reflection paper, there's a discussion about how they uh, came to this decision to have a single type instead of different types. So feel free to have a read at that. Now, just with the reflection operator, we can start to have some fun and start to use some meta functions. What this reflection operator doing is simply giving me a reflection of int here, and I can then use some meta functions to operate on this reflection. Let's have a look at an example that we've done before. So in this example, or actually a bit more sophisticated than that, in this example, what I'm doing is I'm iterating over the enumerators of the colors enum that I've defined before and printing each of the elements. So let's say the enum had red, blue, and green. What I want to be able to do is print each of the elements red, blue, and green on standard output. Now, there's a few things going on in this example. Let's have a look piece by piece. The first thing is the reflection operator. What it's doing is it's giving me a reflection to the enum. And now, as soon as I use this operator, I'm in the reflection domain. In the reflection domain, I can use some meta functions. In particular, the stood meta enumerators of function. This returns a list of reflection for each of the elements in this enum. So what this returns is a list of each element, but not the element itself. It's a reflection to each element. That is an important distinction to make. And to the reflection of each element, I can use another meta function called identifier of, which takes in a reflection and returns a string view, which is the identifier of that reflection. So with this, I'm simply able to now iterate over a list of reflection of enums, or like list of elements in that enum, and print out the string corresponding to each of the elements in the enum. Now this is quite powerful already. Uh, Before C++26, we had to do all these like macro logic and various other boilerplate code just to be able to iterate over an enum or convert an enum to string. You can see just in 3 lines of code, we are now able to iterate over an enum and print each of its element as a string. There's a few other things going on in this slide, so I'll talk a bit more about that. What is this to define a static array doing here? I'll wait for like 10 seconds in case anyone already familiar with reflection or knows why we need a to define static array here. If you want to answer, please feel free to raise your hand and I can unmute you. Okay, I think it's a tricky question. It's not very straightforward. It wasn't straightforward for when I started looking at reflection. But one of the people have answered, I guess it's some context per function that constructed array of reflection. And that's exactly right. Thanks for the answer, Krasar. Uh, this is exactly what it does. But why do we need from like a meta function that returns already a list of reflection? We saw that stood meta enumerators of is returning like a list of reflections here. Why do we want to define a static array out of those reflection? Uh, this is now this is where understanding how reflection exactly is implemented in C++ becomes a bit more important. Uh, the compilers in C++, the compilers have a representation of each of the types or variables and all the entities. Now, reflection is basically um, giving access to these representation that compilers store. So the compiler already has this list of enums while it is compiling the code, and stood meta enumerators of gives access to this list of enums. But if we want to list once the compiler finishes the compilation of the code, this representation of the list of enums is gone. Like the compiler is completed. It while it was compiling, it made this list, allocated some memory. But now that compilation is complete, this representation of list of enums is gone. Now we have a final .o file, or like the final compiled output. What we want to do is store this list of enums which compiler generated during compilation and have it available at runtime, because ultimately we want to be able to use this list at runtime to print the identifier of each element. So defined static array is essentially providing runtime static lifetime for a compile time meta list. It's asking the compiler that, okay, you have this list of reflections or list of representation of the elements of the enum. Please allocate some static lifetime to this so that this can be used at runtime in order to print the element of each enum. The final thing that might be new in this example is the template for and const per here. This is something called expansion statement, which is also being introduced in C++26. I won't go into too much details of this in this talk, but what it is useful is for compile time repetition of a statement. You can imagine a tuple having heterogeneous types. For example, a tuple may have an int, char, and double, and there's no straightforward way to iterate over these heterogeneous types right now. And this is where something like a template for statement comes in handy. In this example, why this is important is because all the meta functions, the reflection input that they take has to be const expr. So when I call identifier of C, C has to be const expr here. So template for, which is this expansion statement, provides const expr access to each element, and that is why it is important here. I have a question. With the reflection operator, you enter the reflection domain, but how or when do you leave that domain? Thanks for the question, David. We'll in the next like 3 or 4 slides, we'll talk a bit more about it. And that's where the third pillar of reflection comes in, which is the splicing operators. Now, before I go into splices, I do want to stress a bit more about how reflection can be implemented by compilers. And this is not a standard way of, or like this is not something that the C++ standard commands. This is up to compilers, but it, but a most likely way of implementing reflection in compilers would be this, and this will help us appreciate how reflection exactly works and why we need to define static array to define a runtime um, to define a runtime static lifetime for the reflection that we are working with. So, quick detour how reflection representation might work in compiler. Imagine I have this class R, then I have a reflection res1 for the class R, and then what I'm trying to do is I'm printing whether the class R is a complete type. Is complete type basically just checks whether the class or the struct that you're providing has been both declared and defined. Like in particular defined, is there a definition for the class already seen? With the definition, the type becomes complete. So in this case, it's going to return false. That's expected. There's no definition right now. There's only declaration. So I'm using the reflection to check whether there's a definition, and it returns false. Makes sense. But let's say in the next line, I now complete the class. I define the class with an int a, and then I get a new reflection of the class, res2, and then I use this new reflection to check again whether the type is now complete. Stood meta is complete type. And then lastly, what I'm doing is that I'm using the original reflection that I had before, res1, and I'm checking is complete type again. Any takers for what this would return? So we know that the first one prints false, but then print2, would it be true or false? And print3, would it be true or false? I'll again wait for a few seconds for people to answer. And in the meantime, we can have a look at it in real time. Okay, so I revealed the answer while having a look, but okay, someone answered print2 is true, print3 is false, and I think someone else also answered second res1 is still false because of context mirror. What it actually prints is that we already know that print1 is false. That's expected. Print2 is it's true because now that I've completed the type, I'm getting a new reflection of it, and then it prints true. I think that's expected because now the type is completed. We're getting a new reflection. It should print true. But the third one is interesting. I'm using the same reflection that I defined before when the type was not complete. And if I call it after the type being completed, using the same reflection, if I call stood meta is complete, now this returns true. This is a very interesting example. This is inspired from Inbal Levy's talk in CPPCon 2025. I'll highly recommend that talk on reflection. Um, and this example kind of demonstrates how compilers might be implementing reflection. So while the reason it returns true is because while the code is being compiled, compilers store abstract syntax tree, which is a representation of the code. And ultimately, you can think of reflection as like a reference to one of the nodes in the abstract syntax tree. And just to look a bit more into it, let's consider this example where I have this C++ code. In this, I have struct foo. I've defined a struct, and then in my main class, I'm defining an object of foo and another int a, just an integer a, and assigning it to 0. So how would an AST or abstract syntax tree of this program look like? Um, the AST would look something like this, and it's pretty easy to see this in Clang. Actually, you can have a look at the compiler explorer link later. And what the AST represents is a representation of this code, and it has various nodes for each class, each variable. For example, I've highlighted the struct foo definition here in the AST. And then at the bottom, you can see the var declaration of the integer. You can think of reflection as a reference to this AST. So in the previous example, when I defined res1 as the reflection to R, instead of thinking of it as a value, which is like a snapshot of the representation of class R at the time, think of it as a reference. So when I did print1, when I checked that the res1 is complete type before it is actually completed, it prints false. That's expected. But then at a later point, if the type is completed, then the reference to it's still the same node in AST. So it's just that this node in AST now has the complete type. So if I access at the end print3, which is using the same reflection to check whether it's complete type, it now returns true because it accesses the same the same node in AST. That's a good way of thinking about it. And the reason it's not snapshotting each time, or like it's not based on values as opposed to references, because that would be like that would, I think, a bit more complicated to implement, and also not very memory friendly. With that, let's look at the last pillar of reflection, which is splices. The splicing operator produces a C++ expression evaluating to the entity represented by the reflection R. Type name of the type name with the splicing operator produces a type specifier. Similarly, template with the splicing operator produces a template name. And to show you an example of both type name and template, consider this where we have a reflection to the type int, and then I can use that reflection. With the reflection, I'm in the reflection domain now. Now to go back from the reflection domain, and in order to use this reflection in my code, I can use the splicing operator and use, for example, type name in this example uh, to get a type out of the reflection. So in this case, it's a very simple example where it's just reflecting int, and then with the type name and splicing operator, it's just splicer operator, it's just giving back the int. Similarly, I can do something like this where I have now a reflection of the colors enum. Then I'm calling a meta function enumerators of and indexing the 0th element. So if you remember, enumerators of returns a list of reflections of each element, not the element itself. So given I have the list of reflections, I access one of the reflection, say the 0th index, and now in order to get this value back and like use it as a actual enum type, I have to splice it back to the the programming domain, and that is where splices come in handy. With that, let's have a look at some examples using reflection. We've seen previously an example of enumerating over a list of enums using enumerators of and then printing it out on standard output. But let's try to build enum to string. And I'll do a quick time check. Okay, I think I've got enough time. So this is how enum2 string would look like. Let's say I have this method enum2 string, and it takes in an input enum, some type name e, and we can reflection library, like the reflection support in C++26, also provides a lot of new type traits, and you can use those type traits to constrain, for example, this type name that it is indeed an enum. But I won't go into too much details about those as of now. But if you look at the reflection paper, there's lots of type traits, and I highly encourage looking at the reflection paper. I think it's very well written. It's beginner friendly as well. So that's something to definitely consider. But back to the example, what we want to do is convert an enum to a string. We've already seen most parts of this example before. Uh, what we're doing here is getting the enumerators of the enum using the reflection of the enum, defining a static array to ensure that there's a static lifetime. But then there's this new part where I'm comparing the enum e, which is the input parameter, which is a parameter to the function, with I, which is like, so I'm comparing if e equals I, then print the identifier of I. So if my enum equals one of the enums in the list, then print the identifier of that. Otherwise, just return unknown. Question to everyone: would this program compile? Given I'm asking, it's already a bit of a tricky question. So I let me say this program won't compile. But what is the issue with this code? A few seconds for anyone to answer. Okay, thanks, Mustafa. That's exactly right. So Mustafa said I is a meta info while e is a value, and this is exactly where having an understanding of the reflection domain versus the the programming C++ code domain becomes quite important. In this example, we are iterating over a list of reflections, and I is indeed a reflection. We cannot simply compare e, which is an enum value, to I, which is a reflection type. So what's missing here is simply the splicer operator, and uh, with the splicer, I convert back it to an enum value, and we can then simply compare, and this code then compiles and returns, and allows us to get an return a string corresponding to an enum. Compare this to our previous implementation, which was like so much macro logic, and at least like 50 lines of code. This is basically just 5 lines of code, and this shows our demonstrates the power of reflection in C++26. Let's try to do string to enum now. Again, something similar to enum to string. And this is how it's going to look like. So now we want to do the opposite, where the user inputs a string and a enum type name. What we want to do is get the enum out of the string if one of the identifiers of this enum or one of the elements of this enum matches the string. Again, we start off with reflecting the enum, get the enumerators of, define a static array, and then iterate over the reflection of each element. Then if what we do is if the string that user has input is the same as the one of the elements of enum, we return the enum itself. Otherwise, if none of them matches, we return std none out. Again, if you look closely, this has some errors as well, and it's important to understand the reflection domain and the value domain. The errors, what I was missing in the previous slides was basically an identifier of, and again, the splicer operator. What I want to check is that if the string is the same as identifier of one of the reflections, and if it matches, I cannot simply return the reflection. We have to use the splicer operator to get a value out of that. And you can again see this is almost like 5 or 6 lines of code and allows us to do such a powerful thing, which is string to enum. The reflection support in C++26 is very vast. Although it's still like the beginning, as people say, I think it's still very rich. There's a lot of meta functions. For example, identifier of that we've seen a couple of times, parent of, basis of, members to get the members of a struct, static data members of, non-static data members of, enumerators of that we've previously seen a couple of times. And then, as I mentioned, a lot of predicates, which is a lot of type predicates. For example, is public, is virtual, is enumerator. So is enumerator is something which we could have used previously to constrain the type name E that was templated. Someone asked a question. That means that enumerators of returns the enumerators in the correct order. So enumerators of would return it in the order that's defined. So the correct order might be, I guess the correct order is a bit arguable if you define it, say enum colors red, blue, and green, and if you give the red value -2, -1, 0, then actually that's I'm a bit unsure about this one. Actually, would it return in the? It should return in the value that you're providing. So, for example, if you have have an enum called enum class colors, red, blue, and green, and you assign red the value -2, blue value -1, and then green value 0, I think it should return by the value. So it would return green, blue, and red. But this is something we can pretty simply check out on Compiler Explorer. We can have a look in the Q&A. But that's an interesting question. Thanks for that, David. So the next example I want to take is of a class formatter. What we want to do is we want to format or serialize a class, and the output that we basically want to print the data members and their corresponding value, similar to what we saw in Python. Like by calling vars on an object type, what it was able to do was it was able to print the data member and the corresponding value on standard output. So we want to do something similar in C++, and this is a very basic example of being able to serialize a class. And we'll see soon how simple it is with reflection. So the first thing we want to do is print the identifier of the class itself. So the first line is in the format function. The format function is taking a type T, which is, say, a class or a struct, and it's printing the identifier of the type. So it will print the name of the class. Then we want to iterate over the data members of the class. In order to do that, we can do something like non-static data members of, which is again a meta function being provided. And always important to provide runtime static storage for that. So we'll get a static array of non-static members of the reflection. Then with that member, we want to access the name of the member and the value of the member. So the name of the member we've seen a bunch of times already. It's simply the identifier of meta function, which returns the name. In order to get the value, this is a bit more nuanced. And what we want to do is our class is taking an object of type T. So we want to access the member mem of the object of type T. Now, if I do t.mem, that won't work because mem again is a reflection. I simply cannot do t.mem by accessing the value. Instead, so this is the wrong implementation. Instead, what we have to do is use the splicer operator to get back the value type from the reflection, and we need to do t.splicer of mem. And with this, simply we're able to iterate over the data members of the class and print out their name and the value. Oh, one thing which is a bit more nuanced as well, but I won't go into too much details of this, is non-static data members of expects and access context, which is things like, so do you want an unchecked context or unprivileged context, which will just return the reflection of everything, including public data members and private data members? Or do you want the context that the current scope in the code has access to? So that is what the access context controls, but let's not worry too much about it. Just to have a quick look at the output of this, let's open our favorite compiler explorer again. And you can see I have the foo class here. It has a member int a, char b equals x. And what I'm printing is I have the format method, and simply it's now just with like let's say 6 lines of code, it's able to serialize the class. This is a very simple example of serializing, but it shows you how powerful reflection is. I know there's a bunch of questions in the chat. I think we're almost running out of time, so I will take all these questions in the Q&A afterwards. I'll be there for a few minutes, so feel free to ask there. The last thing that I want to show is generating code with reflection. And all the previous examples that we've seen have been basically examining the code with reflection, and C++26 provides a very rich support for that. There's also some support for generating code with reflection. It's still in its nascent stages, but we can do a lot of things with just that. So the meta function that's used for generating code using reflection is define aggregate. Define aggregate takes the reflection of an incomplete class structure union type and a range of reflections of the data member descriptions and completes the given class type with data members as described. So the first the first parameter that define aggregate takes in is the reflection of an incomplete type. So you declare a class, say class foo, then you provide a reflection to that class as the first argument. The second argument it takes is a list of reflections of the member descriptions. And in order to provide the reflection of the member description, there's another meta function called data member spec. What this data member spec does is it returns a reflection of a data member description for data member description for a data member of a given type. You can see there's 2 arguments to this. First is the type, so that is the type you want, say int, char, bool, and it is a reflection of the type. And the second is data member options. In these options, you can provide things like the name that you want for this data member, or the alignment, or the bit field. And let's have a quick look at an example for this. So say I have this incomplete type struct person. I want to now generate a class using reflection. I have to do this in a const-eval scope because again, everything has to be at compile time. What I'm doing here is using the define aggregate meta function with a reflection to person, so reflection to an incomplete type, and then a list of a list of data member specs. Each data member spec takes a reflection of a type and then an optional description. So I'm giving the names here to each of my data members, name, age, and weight. What this will produce is a struct person as a complete type with these three fields: the name, age, and weight. And this is how we can define new types using reflection in C++26. So what we're doing now is using reflection to generate code. So it's not just examining code, but we can also generate code using reflection. I think an example of this is implementing a very simple tuple, which is, I think, a very powerful example to show how generating code using reflection simplifies the code bases and a lot of boilerplate that had to be done before. And all these things were achieved using very sophisticated metaprogramming, which is what reflection simplifies quite a bit as well. So let's have a look at an example where we're trying to implement a simple tuple. Before C++26 or before reflection, a tuple would this is what a simple tuples implementation would look like. Given we just have a few minutes, I'll just show you the whole implementation, and you can see it's like essentially what we're trying to do is we have this class tuple. It takes a variadic template, variadic arguments, types t's, so a bunch of types. These could be heterogeneous types. Then I'm trying to implement this tuple where I want to store each type inside this tuple. So if I have a tuple of int, bool, and char, I want the user to be able to store an int, bool, and char in this tuple. And this is how a metaprogramming implementation would look like. I we'll have an incomplete declaration of a declaration of class, and then a specialization which takes the first type t, and then the rest of the variadic pack t's, and we'll define the struct as a member with the type t, which is called head, and then a tuple of tails. So essentially, it will be a struct with just one member, one direct member in it called head, and then a tuple of the remaining members. So it's using recursive implementation to implement it. You don't have to bother too much about the implementation, but just the fact that um, it's a bit tricky to wrap your head around the implementation. It's not very straightforward. We need to use a lot of metaprogramming and um, templating magic to achieve this. And if I open this in Compiler Explorer real quick, what we will also be able to do is have a look at what this code actually generates. If I zoom in a bit and run this, you can see I have this step tuple implemented using metaprogramming. Then what this shows is the instantiations of my tuple. So you can see I have a tuple of int, char, and bool. This is the instantiation. What it does is it creates an int head and a tuple of the remaining types, which are char and bool. Then we'll see instantiation of tuple char and bool. It again has a char head and the remaining tail. And finally, I have the tuple bool, which is just the bool. So there's a lot of metaprogramming and templating magic that goes behind it. And next, I want to create a tuple element utility, which basically takes in the index of a tuple element we want to access and returns the type of that element. So all it does is give me an index, and I'll return you the type corresponding to that index in the tuple. So it takes me 2 slides and a lot of template metaprogramming to implement this without reflection. With reflection and define aggregate, the implementation looks simply like this. On the left, I have a struct tuple. Inside this tuple struct again has a variadic template type t's. What it's doing is it's declaring a struct storage, an incomplete type, and then I'm defining an aggregate with the reflection of storage and a data member spec of the type t's. So I'm simply taking a reflection of type t's, expanding it using like a variadic pack, and defining an aggregate using those type t's. Now, this implementation will produce a tuple type, which is completely flat. In the previous tuple type, we had to do some recursion where we had a head and a tail, and just to have a tuple of int, char, and bool, it instantiated 3 different structs. In this case, it's a simple flat tuple. It's easier to reason about. The code obviously fits in half a slide as compared to a lot more in the previous implementation. And then similarly, tuple element in tuple element on the right side, in order to access the type of an type using an index to the tuple, what we can simply do is we can get the array of the reflection of type t's. So tuple element takes in a tuple having type t's. What we can do is get a reflection of the array of type t's and simply then access the ith element in the array of the reflection and splice it back to get the type. There's several examples. You can have a look at the slides in more detail later, but it's all about appreciating how simple the reflection makes all these things. To recap, what we've seen is reflection is the abilities of a program to examine itself. We've seen the 3 pillars of reflection operator, which lifts expression into the reflection domain, meta functions, which are used to operate on reflection, splicers, which produce a C++ expression evaluating to the entity represented by the reflection R. And I think this is the superpower of C++26, examining and generating code. And I hope that you were able to appreciate this as part of this presentation as well. There's a bunch of resources that I've added in the slides. A lot of the slides were inspired by all these talks. Enbal Levy did a great talk on Introduction to Reflection in CPPCon 25. David Vanderwood, which is also one of the persons behind Reflection paper, did like a indie talk. And Barry Revzin did a very interesting talk, bit more on the advanced end for reflection. And then the paper for reflection, which is, I think, a very well-written paper, definitely worth looking at. With that, thank you so much for editing my talk. Hopefully, you got an appreciation and a gist of reflection in C++26, and you are as excited as I am for it. Thank you so much.